inviting me here to give this seminar. And am I audible? Great. Okay, so what I'm going to be doing today is talking about data mainly in astronomy. I'm an astronomer by training, but as Paulus mentioned, for the last 15 years I have been working on large sky surveys, which means that I have been dealing with large amounts of data, which meant also that I had to learn a large number of statistical techniques, a large number of computational methods. So I'll also be mentioning a recent project that I have gotten into. It is related to cancer bioinformatics. On the surface, it may seem quite different from astronomy data, but what I'm going to show or mention at least is how deep under they are quite similar to each other in terms of being able to apply similar kinds of methods to them. So if you take one thing from this, then I would like to mention that it should be that for many catalogs, not only are the number of rows increasing, that is the amount of data in terms of the length of a table, but also because of the number of types of observations, the number of columns are increasing. So we have more number of observables, and connectivity between these variables is a very important thing. Not all of these variables are independent of each other, so they are not independent dimensions, but they are different subtly, and learning how they are related to each other, or some of them are related to each other, is where the domain knowledge comes in. So what I'm also going to be saying is that though we have large data, though we have beautiful machine learning techniques, that doesn't mean that your domain knowledge or your expertise as a human can go away. In fact, it becomes even more important, because in that data there is a lot of redundancy sometimes, then there are a large number of hidden features, which if you have a little bit of domain knowledge, that becomes even more interesting. So I'll be coming to that soon anyway. So in astronomy, as I mentioned, we have very large amount of data, and normally big data are described in terms of various V's like volume, and in astronomy we have been going from now terabyte to petabyte and soon to even larger exabytes and zettabytes in about 10 more years or so. Then in astronomy, the kind of astronomy in particular in which I work, it is also very important to do things very quickly. I work in transient astronomy, and I'll mention what transients are, because this is about domain knowledge, so I will tell a little bit about some of the terms that I'll be speaking about later. But so we need to do real-time analysis. Some of these objects are such that you have to do some follow-up observations very quickly before they fade away in order to get any science out of that. And then there are various things like veracity. There are as many as 400 different classes of transients, and I see that one word has gone missing there, but it's variables or transients. And we normally use large number of time series. And again, time series that we have in astronomy are quite different from time series that you may find in the financial domain, where every morning at 8 a.m. you have got a data point, and that way it becomes a very regular time series. In astronomy, unfortunately, it's not like that. So we have to invent new kinds of methods to work with them. And then we have error bars, which the statisticians like very much, and sometimes we have to get to fuzzy classification or to characterizing the data before you can get to classification, because sometimes it's easier to say what a particular kind of astronomical object is not rather than what it is. And once you eliminate a large number from the 400, from what remains, then you can try to figure out which observations are good to be taken, which will then further discriminate between the different remaining classes. So this is again a broad classification that many of you may have seen in different ways. So you have got computer science and efficient algorithms and optimization, you have domain specific knowledge, and you have got mathematics and statistics. So if you combine only the top two, that is what gets you to machine learning. But it is the domain specific knowledge which then brings you to the intersection of all three circles, which is the data science, and that is where we should be going. And the other thing that I would like to emphasize is that there are many softwares that are now available. So one should not try too much to reinvent those wheels unless you are doing something which no one has done before. You are working on some techniques that no one has worked on before. Some of these techniques available in Python and MATLAB and R are there, which you can simply go and start using with only a little bit of effort. So here is just a schematic of various machine learning related things from the Python scikit-learn package, where you can do regression and you can do unsupervised learning, you can do supervised learning, and so on. So again, you should be using a lot of the tools that are out there. So what are the transformations that have been happening in astronomy over the last several years which allow us to make use of these various techniques? So earlier, an astronomer used to go out to an observatory, decide on some kinds of objects to observe the data, come back with the data set, analyze and publish. But now what has changed is that we have sky surveys. So rather than taking small pointed observations, you can look at the entire sky. Not just that, you can look at the sky multiple number of times. So with CCDs, the charge coupled devices, which you also find in your cameras, you can take rapid images. The same thing has become possible in astronomy, which means that you can now start seeing objects that change in brightness, much like what you would see people moving, not exactly that because the brightness changes are on different scales and different kinds of objects exist. But in principle, what was not possible several years ago is now becoming possible. So here are two images where you don't see anything in a co-added image. This is an image over a large duration, but in these two individual images, you see something at the box in the middle, and those are the kinds of objects that I have been interested in. So digital movies is where we are moving to. So in general, this transient that I'm talking about, what it is exactly. So I worked on a sky survey called the Catalina Real-Time Transient Survey. The basic reason the survey came into existence was to look for asteroids, and for that what they do is that they take 4 images that are 10 minutes apart, and that way if there is an asteroid, you'll find the asteroid moving, whereas the rest of the objects that you see in that image are static. You don't see them changing in position. But then what we started doing is that we started taking all those data and started looking for other kinds of interesting objects in that, and those are transients which change in brightness to a great extent. More or less you can have different deltas there within a short time span. Again, that delta time, that short can be minutes for some objects, seconds for some objects, or days for some objects. So that depends on the science and the nature of object. So what I'm showing here is a light curve. A light curve is essentially a time series. On the x-axis you have got time, here it is in days, and on the y-axis you have got brightness. The brightness is in logarithmic scale. This is magnitude, so smaller magnitude number numerically means a brighter object. And here you see that over several years this object is fairly constant, but then within a short amount of time it shoots up in brightness by a few hundred times. So this is a particular kind of variable, a flaring star. So there is something happening magnetically on it. So you have got a fairly consistent object and then suddenly this flare. It's very good that our sun is not the kind of object where this can happen. Imagine if it were to brighten not 300 but even 3 times, then things will be pretty bad. But there's one kind of transient, and we look for all kinds of transients. So again, CRTS, the Catalina Real-Time Transient Survey, started as CSS. It still does that. They look for asteroids, and we have been able to actually find asteroids before they hit Earth. So there have been 2 objects so far that were predicted. These were small, thankfully, but one of them, then people could go out into the Sudan desert and actually collect parts of that. So this is the cheapest recovery mission that one can do, rather than sending a spacecraft to an asteroid and getting anything on that. You can receive it that way, but hopefully there won't be too many asteroids that will be coming towards the Earth, but there are projects that allow us to look for those. So in order to look at all these asteroid data, CRTS has been covering much of the sky. So this is how the sky is displayed here. On the x-axis you have got RA, which is like longitude, and on the y-axis you have got declination, which is like latitude, and this dark portion is where our galaxy is, and we leave that out because that is the area where there are just too many stars. We cannot do much separation of those stars, so we stay away from that. And the kinds of transients that you see are shown here. So again, in the pairs of images, all you see that some object has become brighter, and just from the images you cannot really tell what kind of object it is, but there is a variety that is possible in those objects. And what it is, in order to find that out, you need some ancillary data, some other catalogs from different wavelengths and so on, and then you need to combine them in imaginative ways using computational methods to do that. And it's the quick classification of these objects that is important, because once that object fades in a matter of say minutes or hours, if you go and observe it again, all that you are going to see is how it was before, not really what it was doing when it really brightened up. And that is why it is important to be able to classify these quickly convey it to the rest of the world so someone else can go and observe it using, say, take a spectrum of it, etc. And then the number of possibilities is huge, the number of classes that exist. So there can be intrinsic variability or extrinsic variability. Extrinsic variability is because of, say, eclipses. So some object eclipses another object, it suddenly becomes either brighter or fainter, and then that is not really something happening inside, whereas intrinsic variability is where an explosion is happening, or on the surface there are some variations happening because of which you see. And each of them can be split into many different ways. Again, there are objects that are both extragalactic, outside our galaxy, as well as galactic, and objects that are within our solar system as well. So we have to do characterization before one can get to classification. Taking a spectrum is the final word if you manage to get a spectrum of it, which is much more expensive, of course. So here are two spectra that are shown. On the x-axis is the wavelength, and on the y-axis is brightness in some units. If you are managed to get a spectrum, that is how the light is distributed in different wavelengths, then you really know the nature of the object in a very specific way. But that is very expensive. So what one tends to do is try to get broadband imaging, that is a filter which covers, say, a large part of it. And so you could have, so this is a filter, and then you could add up all the photons in the filter there or in the filter there, and just have those few points and see what it is that those few points can be telling you. And for most objects, that is the only kind of information that we have. In fact, CRTS doesn't use any filters. All it has is an open area, and that is from which all the data is received. Then there can be specialized things like polarization, but for most objects it's not available. But there is also contextual information, and that becomes crucial, and again that is where domain knowledge comes in. So as I mentioned, you have our own galaxy, which is called the galaxy in astronomy, and most stars live close to that plane. So if you happen to observe an object whose galactic latitude, that is distance from the plane of the galaxy, is low, then without knowing anything else, you can attach a high probability that it belongs to our galaxy. Whereas if you find an object, a transient, which is at a high galactic latitude, which has changed in brightness, then again, without knowing anything else, you may be able to say that it's more likely that it is an extragalactic object. And these individual bits of information, then you can start combining together in a statistical fashion to do that. And because, as I said, we're interested in announcing our transients to the world in quick amount of time, we developed various techniques. This is Sky Alert, where what we do is that we use various Jabber-like protocols so that people can subscribe to our servers, and whenever a transient goes up, there is also an iPhone app, you'll be notified about the existence of transients, and then you can do with it what you want. You can have automated telescopes that subscribe to these feeds, so the telescopes receive these transient events, and then they can go out and do that. So this is what I was meaning when I said one can use priors that are built, and these are statisticals, and I'll come to the definition quickly. So this is change in magnitude over one day in a certain band. So if that is the only thing that I were to know in a large number of objects, that is if I observe a large part of the sky tonight, and I observe it again tomorrow night, and the change in time over one day, what is the change in brightness that I have for every object? And if I get this kind of bimodal observation, I have combined everything here, but then I can do it as for different classes. I can have something called cataclysmic variables, or I won't do that, but say planets and everything. And then I can split this histogram in different ways. And then if I have a single observation using those histograms, then I will be able to say which class it is likely to belong to. And that is what we combine, say, using Bayesian networks, and I'll be coming to Bayesian networks soon. So one has a large number of parameters available. Many parameters can be simply contextual parameters because of the position of the object. Many of them can be specific observations that you do as a part of the time series, and you can get more and more characteristics from time series. Some of them can be as simple as amplitude, which means in your time series, what is the brightest point versus what is the faintest point, what is the difference between them, or simply what is the median buffer range %, or you can have simply standard deviation or specifically defined ones like Stits and J Stits and K, which are available in literature for tens of years. You can also define new parameters, of course, and this is where again domain knowledge comes in. So we'll be seeing some supernova and non-supernova classification using a very simple method soon. And you can define additional parameters which depend either on whole curve measures or only part of the curve, because for some time series where the intensity rises, you may be interested in only that part perhaps, not the entire time series. Then again, what I mentioned is that we normally don't have regular time series. So you may want to use a method like Gaussian process regression, which first regularizes the method. So you now have a time series at a very good frequency, and then you can apply various different methods to that. So when one combines all these different kinds of features, and these then become the dimensions of your mathematical space, the picture can start looking a bit complicated. And here I have tried to show, this is Adam Miller's slide. I have shown several 20 different parameters or 20 different features that we extract from light curves, and there are of course many more, and we don't want these busy slides, but this is just an example that we are really trying to use a large part of the light curve in many ways. And then of course some of the mathematical features that we define, you simply cannot show it in a simple manner with an arrow and so on. So when one comes to using something like Bayesian networks, you start with a few definitions that are fairly basic, like here we are talking about just axioms of probability, and you of course all know that, so I'm just summarizing that in a slide, that the sum of all probabilities, if you consider all possible happenings that are possible, you get a sum of 1, and complement is 1 minus that, and so on. So basic principle. Similarly, if there are mutually exclusive events, then the union of probabilities is the sum, same as the sum of the individual probabilities of all those objects. And it is from these that one can go ahead and define things like likelihood, prior, and posterior. So prior in particular we have used earlier, where what you are doing is that you are saying P of data given parameter. So what we expect the data to look like when we have certain knowledge about it, whereas posterior is when what we expect about the parameter given the observations that we have. So we start with various priors, and then we combine those priors into getting this posterior information. And then one has to remember that when we talk about trying to find out about the unknown, it is not just based on data and knowledge, but a large number of assumptions may have gone into that also. For instance, there can be assumptions like all the objects that I see in the sky are in fact astronomical objects, but that need not be true, right? We are assuming that we won't be seeing aeroplanes, that, or it is not in the path of an aeroplane, or that we are not seeing meteors and so on. So those assumptions many times are not stated, and typically this is how the statement goes, that P of unknown given data and knowledge. But always in these methods, the Bayesian methods, you have to remember that there are assumptions that have gone into it, and at some place you need to note them very well and maybe even revisit them at some point. So conditional probability is what one starts using in Bayesian networks. That is, given something, what it is that is going to happen. And again, taking a simple example, if you have a single dice, there are 6 different possibilities, and so omega there represents all the 6 different possibilities, and you are asking yourself, what is the likelihood of something particular happening in general if you have a throw. So A I have defined there as 1, 2, 3. So what is the likelihood, what is the probability getting 1, 2, or 3 with a normal die? Of course, there are 3 different ways you can get 1, 2, 3, 1 or 2 or 3, and 6 ways of for the die, so it's half. And then you can start combining them in different ways. If you already have a knowledge, say B, that it was either 2 or 4 or 6, and then you combine that with A, then you know that 1, 2, 3 is what you're looking for, but you know that it was either 2 or 4 or 6. So combining the two, then you can, if you re-ask the question, then you are asking yourself that A intersection B is only 2, so that becomes 1/6 of that. But given that you already know that it is an even, what it is that you are looking for, so it becomes then 1/3, given that A intersection B is only 1, and you have the knowledge already that it is one of the 3. So what's the likelihood that it's 1, 2, or 3? Becomes 1/3. So those are the things that we start combining from all the priors that we have. And then we go on to build a Bayesian network. And a Bayesian network is where you've got different kinds of variables, and you connect them. The connections are directional, and you don't have any cycles. That is the main thing about a Bayesian network. And once you have that, then you can follow these inferences, the simple probabilistic modeling that we just saw in a very simple way. Now here I have a diagram, a simple Bayesian network. Grass is wet. If it either rains or there is sprinkler, it's a nice sunny day outside, unlike yesterday. If it was yesterday, we would have been sure that it's the rain that's wetting the grass. But today I actually saw a few sprinklers wetting the grass outside. And then again, these kinds of bits of knowledge that go into the priors of making that. So how many times is the sprinkler on? So those bits then start defining for you that if you go out and find the grass to be wet, then is it because of rain or sprinkler? You can easily start attaching numbers. And of course, what we do is that do it on a much, much larger basis. And this is how it comes about. So here, the set of parameters that I showed earlier, this is where all of them will go. There will be some incidental parameters like what the galactic latitude is, what are the different colors from different filters, what are other observable parameters, is there a radio source nearby, is there a galaxy nearby. And then those will get combined to tell you what class it is likely to be. And again, this is a naive Bayesian network where all the parameters are simply going up to 1. But if you also bring in phenomenology, try to understand the physics behind them, then it becomes a more interesting Bayesian network. And that is where all the methodology really comes in. Because the simpler naive Bayesian network, you can also use other methods to do that. The interesting thing about the full Bayesian network is that you can use your data to define the network. That is, you do not necessarily always have to come up with the network yourself, but many times the data will advise how the network should be. And that is what I found to be the most interesting aspect of a Bayesian network. That is why I decided to use them a lot. But then I was in for a little bit of surprise, especially given the number of parameters that we have. So Bayesian networks are fantastic. They're fully probabilistic. They're perfect. They can deal with missing parameters. They can deal with missing data. So one thing that I should tell you, I had a formula here which I didn't go into. So what I'm doing here is that suppose I have got 100 different parameters which form my table, the 100 different columns, and I want to use all of them, and some of them are connected. Then what the simple probabilistic methods allow me to do, probability-related methods, is that I can clump them in different ways so that if I don't have any of them, I can just leave them out. So whatever remains, I can play with only those parameters for any given row and still get meaningful results. And so that is why it was interesting. But what happens is that the number of parameters, as they start growing, you just can't have your Bayesian network calculate or have your methodology calculate the network from data easily. The amount of time it will require just goes super exponentially. And so there are many different ways you can get around that. You can build smaller naive Bayesian networks, which are not as powerful as the fully Bayesian networks, or you can build use some semantics or expert knowledge that can go into that, or you can use smaller networks where single winners from several naive ones can start coming in. Because again, ideally the data defined network, so you should be given all your columns, all your rows in a single programming loop for your Bayesian network, but that just is not going to work because of the time that it's going to take. So ideally, what we want is a single network of this fashion. That is really the aim, where all the parameters go into it, and then you have got one class which takes some of those parameters and another class which take another subset of parameters, a third one, and so on. And those all connect using phenomenology at the top, depending on various constraints. But what you have to do is smaller networks. And that is where, again, the domain knowledge comes in. So let me talk about a specific such case, supernova versus non-supernova. A supernova is an exploding star. And again, thankfully, these stars don't explode day in and day out in our galaxy. If that happened, again, we'd be in for a bad surprise. So most of the supernova that we see, and we know thousands of them by now, are in external galaxies, many times fairly far away. But what that allows us to do is have a basic datum that if I see a transient and if there is a galaxy nearby, then there is a good chance that that particular kind of transient is a supernova. If I don't see a galaxy nearby, there's a good chance that it is not a supernova. Of course, many times there are complications that if you were to use a larger piece of glass so that you can collect more photons, then you can start seeing fainter galaxies. So you may have a supernova where you don't see an obvious galaxy, but just because it's farther away. So distance to the nearest star may also be an important parameter. The nearest distance to galaxy, you may have to also make sure that that particular parameter you normalize, because what's going to happen there is that you may have two galaxies. One galaxy may be nearby, there may be another galaxy farther away. You may also want to know which galaxy it is that it belongs to really. and of course the archival light curve that you need. So as I said earlier, we take transients and publish it so that other people can follow them up and tell us. But this problem is getting quite bad. Right now we have got only a few transients to work on, but given newer surveys, that's going to get multiplied in a huge fashion, so there will be no way that we can follow all the transients. And we want to get to the point where we should be able to make most meaning out of these transients without any additional observations. And how to do that is by defining specific new parameters which you can use from existing methods to get answers out. So as I mentioned again earlier, there can be confusion that here we see a transient and there are two galaxies. This is a galaxy here, and one would think that it belongs to that galaxy. But if you look at a very small region around that object and zoom that in, you find that there is another much fainter galaxy there. So sure, it's very likely to be a supernova, but which of those two galaxies it belongs to? So using just these three parameters, we defined a new feature called a prior outburst statistic, which is based on the total time span of the time series and how the individual points in the series act with each other. So all this that this is doing is looking for, say, the median of the time series, then you define a certain number of standard deviations above it, then look for all possible peaks in the time series and how much area is under the curve in those time series, in those peaks, and how many they are within a given time span. And once you define that, we find that using only archival parameters, this particular prior outburst statistic which goes there, and minimum star distance and minimum galaxy distance, which is normalized, which all comes from archives because these archives already exist, you can find out whether it's a supernova or not a supernova to 80 to 90% confidence. So using just archival data, if you define properly a new feature, you can do a lot of science. And this is simply schematically how that particular diagram looks. The other things that we have been doing is that these large number of features, say again hundreds of parameters, hundreds of columns that you have, not all of them are independent. So you can use various methods like the fast relief algorithm or the Fisher discriminant ratio to try to figure out which of them seem to be more important for a given particular set of classes. And once you do that, then you get in return something like the y-axis that you see there, where it is arranged by the importance of the classification that you have for those particular classes. So as I said, the problem is becoming insidious. Right now we have got, say, of the order of a dozen transients every night, and we publish those and some people follow them up and so on. But in a few years, LSST, the Large Synoptic Survey Telescope, is going to be releasing 1 million to 10 million transients every night. That is about 1,000 every minute. So there are going to be that many transients, and what does it say? So 10,000, sure, meaning of order of 10, right? And then, yeah, order of magnitude, astronomy. So I mentioned earlier that we already have the Sky Alert that publishes these events, but it's not scalable. And so what we really need is a more scalable pipeline, which is being built or other thought about, not built yet, because LSST is still a few years away. And we need to think in great detail about all of these. And each of these involve a large amount of data wrangling, data science that comes into the picture, and data methodologies need to come in. So here we start at the top. The dashed box is what this system Antares is likely to be doing, is supposed to be doing, because that is not LSST's, they are not promising any of that. LSST simply says is that we'll give you 1 million transients every night, and we won't do anything else with that. You do with it what you want. That's what the science community is going to do. And then what the science community needs to do is come down to, say, only a few transients, few interesting transients per night, so that they can be followed on. And there is very interesting set of challenges that are hidden in there. So here I show one thing called the moving object catalog. So there are a large number of moving objects that LSST is going to be finding, and those have orbits. And unless you know what orbit a particular object belongs to, if you find the same object tomorrow, you will also call it a transient, and you want to be reducing that number, so you want to be building those orbits. So there are interesting challenges involved there. Then taking other wavelengths also is very important because there is science that is hidden in other wavelengths, so that needs to come into the picture. So it's essentially the list that is there on the left hand side, those should be used, and then one should be coming down to this small or some rate that one can handle, 0.1 rare alerts per image, which is still a fairly large number of rare alerts per night. Again, these rare alerts are something that we don't fully understand, so it is going to be an exciting time. And from computer science perspective, various algorithms that can go into especially the second half here, where up to here, if you notice, we still have the same number of transients, 1,000 per image. By the way, the million to 10 million are not going to include any artifacts. So it's not as if most of them may be artifacts of some kind and you can easily remove them, because that is going to be meticulously done before that stage. So up to here, we have not done any separation, and it's only after here that it comes down to 100 and to 10 and to 0.1, that kind of thing. So there are various algorithms which are going to be developed for that, and some of you may be involved in that at some stage, is where you should be able to plug those into that setup to get interesting results. And this is one of the proposed networks to allow you to do that. So you have various CS related methods that can be plugged into earlier network. There are other things what we do with time series, where you can simply take pairs of points. Now if you have got n points, and if you do something with pairs of points, then what you are going to have is going to get n into n minus 1 points, and you are going to get some interesting patterns out of that. That is still under development. The other thing that we are doing is seeing how sparsification of light curves, we can try to retain as much data as possible. So here, what happens again is that when a transient is found, very little is known about that, and you want to be able to do as much about it as possible. So sometimes the number of points could be 2, 3, 4, and again, something with 4 points is not really a time series, but still that may be the only thing that you may have access to, and what is it is that you can do. So with existing light curves, with known labels, you can try to reduce the number of points and see what you can get. And here what we have is again the large number of features I talked about. Here are two different classes, active galactic nuclei. No, this is actually the same, two different sets of data for AGN, but here is a similar curve where what you have is for AGN and supernovae, and now you see that there are certain parameters which change their nature, like here you got skew and kurtosis. For the two sets, they look quite different from each other. And so those are the bits of information that you can use to define specific parameters for these classes so that they can start distinguishing between the two. The other thing that we are doing with this time series is again using different sets, different catalogs, and how we can learn from one catalog to train another catalog, because every time a new catalog comes in, if we start training, that can take valuable resources. There can be a year spent before you can start getting meaningful results. So here on the top, what you see is a data set from CRTS that I mentioned before. Sorry, the labels are not seen very well, but here we have got several years of data, magnitudes there, and this small area is zoomed in here because there is another data set from the Kepler satellite which takes data almost continuously. So during the time that CRTS takes only a few observations, Kepler can take several thousands of observations, and how to combine the two together is one of the things that's going on, again on the same lines as before. And for combining of parameters from different wavelengths, there are services that have been developed under the virtual observatory. Those already exist. You can use cross matching between the two and get that information. So I mentioned various techniques that one can use related to astronomy, how large data is there, but there are many, many parallels with many other sciences. So one thing that is being done in earth sciences, for instance, is what you have is consider the sensor networks that are available. There is satellite observations of land surface, how the land surface moves is known from various satellite observations. Similarly, there are various ground-based land surface observations. These sensors are sitting on the ground and they tell you about whatever is happening. Then there is a lot of aquifer water level data available. Aquifers are distributed all over and they tell you again what is the water level. There are observations of surface water itself, what's the surface depth, there's soil moisture available. And now you can see that this is immediately very parallel to the astronomy data that we're talking about in terms of different wavelengths. So if I have data in say R band, G band, I band, or infrared, ultraviolet, then having information about water related parameters, snow, water, moisture is the same. Again, the resolutions here are very different from each other for each of these sets. In some case, like the water mass, these are only monthly observations and the resolution is only 300 kilometers. So you have only 1 point in 300 kilometers, so not that much. But it's better than not having anything. So the moment you have a little bit of information, you can start using that. And so these data are now going to be combined in a meaningful fashion. And again, California is going through a horrible drought right now, worse than from many, many decades, and especially the Central Valley is suffering from it. And many of these observations are available there. So that is where we are trying to now combine those data sets and see whether we can advise what kind of water management could be done in the future over the long run to try to best deal with a situation like this. The other thing that I would like to come to, another parallel, is related to cancer research, how many of these things are also usable there. And Boston has been very heavily involved, of course, in cancer research right from the early days. The Jimmy Fund for Cancer in 1948 was started in Boston at the Children's Hospital here. And so at that time, there was a young patient, and his name was Jimmy, and from California, there was a radio show, and Jimmy was a baseball fan, and the entire baseball team at that time walked into his room in the hospital, and that's how the Jimmy Fund started, and then money started pouring in a lot. So the Atlanta Braves, they started life as the Boston Braves long, long time back, and that is when this all was happening, and a lot of cancer research in Boston, of course, continues. So just like there are features within light curves that you can define, similarly you can define what are called the hallmarks of cancer. There are certain properties that are common across different cancers. Though liver cancer is quite different from brain cancer, certain things about the cells that are involved in cancer are the same. What happens is that these cells learn to bring additional blood vessels near them. They learn how to be mobile through blood and go to other parts of your body, or they learn how to become immortal. They learn how to make themselves not be felt, invasive, and so on. So this is from the 2000 paper. Again, Richard Wagner is a very local person. He's from MIT biology department. And what has been happening again is that newer and newer features of cancer are being developed or found out. And this is a recent paper by the same duo, where instead of the 6 hallmarks, now we have about 10, and we are also starting to learn what it is that, how it is that we can start understanding what can be done about this. So EDRN is the Early Detection Research Network. Dan Crichton at JPL is the PI of our part of EDRN, but there are several units all over the country. And what we do here again is use various stacks that are available, open source and so on, and various features are captured just like in astronomy data or earth science data, and you've got lots of biospecimens, and from that you find scientific data sets, and various protocols are defined. And then what happens is that, again, the main emphasis is about data discovery. So starting with collection of data, management of data, the emphasis comes down to how you can discover interesting patterns in these data sets and how the data can be made accessible. Again, in case of biology, of course, you have to make sure that no patient information is released, and then doctors don't want any of their proprietary data to be released before publication. So there are private sets and public sets and all that can be handled with computing. But again, the main point is that there are all these observations available from various data sets, and one can use exactly the same techniques that I mentioned before, using domain knowledge, go in there and try to get gold nuggets out of these data sets. And again, it is a very distributed data set. It's a virtual data set. You can go into the system. So one of the important things again is specimens. So when a new technique is thought about, you are interested in finding out if there are available specimens and what it is that you can do with those specimens. So again, Boston is very closely connected to this Thaddeus Dryja, who's again at the Massachusetts General Hospital. So a few decades ago, he was the first person who started collecting these specimens. And then he works on the eyes. He's an ophthalmologist and eye cancer. So whenever he would hear of a specimen, he would fly out or drive out or walk and get the specimen, and that is how he started collecting a specimen. But now with our initiative, what we are doing is that we have databases of specimens, so people can quickly find out where which specimens are available for all kinds of cancers, and they can go into the data set and get out things of that. So some of these things which can be published properly or they can be shared, we try to share it as much as possible. And one of the rules that we have been trying to follow are how you can make the research as reproducible as possible. So we wrote this paper some time back. Alisa Goodman was the first author, and Merce here in the audience, and I was involved in that. And we are trying to follow that. So when you have a data set, when you publish a paper, giving just a figure is not sufficient. What is important is that how you can reproduce the figure. So if you could give the code with it or the data set which went into making that figure, that goes a long way, because then it's easy for other researchers to be able to modify that. We recently followed that up with our own advice by doing that on a light curves paper where we presented various R methods and how the Gaussian process regressions in that work and so on. And of course, the cancer data too, we are using a large number of machine learning techniques there, using various images that are available, fMRI and so on is something that we are going to be incorporating soon. So there's huge scope for all of that to be done. So what I've tried to do is give you a flavor of the kind of techniques that are there, what kind of data sets are out there, and how there is a commonality between different fields, and you can use the same kinds of methods. What is important is going to the basics, starting from, say, the Bayesian networks, understanding the probabilities, understanding what are the priors that you should be using, what are the features that can be developed. And once you have that, despite big data, despite very powerful machines, very powerful techniques, you as a scientist will remain in control of things, and you will be required in all that. It becomes like the glass bead game where everything is really connected, and you can find out how the connections are and so on. So to boldly classify is where we should be going. I'll just mention quickly that there is a new data center that we are starting at Caltech. It started as of 1st October, in fact, Center for Data-Driven Discovery, and many of the initiatives there try to include different disciplines again. So CACR was the existing center until last month. So this is a new Caltech JPL initiative, and formulation and execution of data-intensive projects. So I had to read it rather than being able to say it, because it's so new that even I don't remember everything from even the name of it, CD Cube as we call it. So I'm going to stop there. I mentioned a few collaborators in the slides, but there are various people who have been involved in all these various things, because it's a huge set of problems, issues that we have been dealing with in order to do the research. So here are just some names. You can come back to that, and I would like to stop with that and leave you here. Thank you.
A great part of this is finding things that you're not expecting. How do you figure out what it is that's important enough if you're not expecting these things?
Right. So the Bayesian networks and even in other methods, what we normally do is that there are two ways you can do things. You can have a classification set we have got where it's a multi-nodal system, multimodal system where different classes are there, and you get probabilities out. So you can have a threshold which says that, okay, if this particular threshold is not met for any individual type, then what I have is not here, so it's somewhere else. So it is marked as such, and then you can try to do something else with it. You can publish it as it is. It's one thing. Even in binary classifiers, then what one can start doing is that ask questions like, is this a supernova, not a supernova? And then again, you'll get probabilities. And if you end up being not a supernova, not an AGN, not a CV, so you have to keep track of that particular branch. And that is, in fact, the rare transients that I mentioned. Most of the objects that we will be interested will be exactly that kind. And then additional data on those can be fed back in? That is a very important question. Thank you for bringing it up.
How do you sort of verify, validate these terms? What bodies of data have you used to validate those
Right.
correlations?
So for we have spectra for about 2,000 or so objects. So as I mentioned, taking a spectrum is the ground truth. So we do say what the objects are likely to be, and for these objects we have spectra, and when we have spectra, that helps vindicate what the observations were, and whether it was right or wrong, that information goes back into the data space. Again, an important function I did not talk about, validation. That is a very crucial step in anything that is done. So we do have labeled sets. Initially, many times though, if you have a very large data set where you don't have enough data, labeled data set, one would start with unsupervised classification, unsupervised clustering, where you make different clusters, and then try to go into the cluster and see if you know any of those objects. Both methods are typically used. So aeroplanes and that kind of artifacts, we remove them first right at the start, because most astronomical objects are, they have a Gaussian pattern, a PSF-like feature. So when they enter the atmosphere, they're going to spread out that way. But there are also asteroids, of course, which leave a streak. So there will be planes which leave a streak, and there'll be meteors once in a while that you see which will leave a streak. So at first order, streaky versus Gaussian-like versus a third type is where the separation gets done. And the third kind are normally removed right at the start. Then the streaky ones, you can get some science out of that, so you keep them aside and run a separate tree on them. And once you come to the Gaussian ones, then you can do your rest of science.
So we're talking about large data.
Mm-hmm.
None of this work I'm involved too is really challenging in the sense that you cannot just put more machines. Or is it something you think that the large data will prevent us from doing?
No, I don't think large data will necessarily prevent you from doing it, because again, going back to this.
I mean, let me ask you this
Yeah.
question. When we talk about large data in astronomy,
Mm-hmm.
it's large data in the image. So nobody in astronomy works on the image, they work on the catalog,
Right.
on the actual object.
Mm-hmm.
Even if you have 10 billion objects that are visible and see, this is like 20 to 30 terabytes.
Yeah, that's not large. So yeah, but
It's not really a large data
Yeah.
problem anymore, right?
yeah, meaning, but if you say go to something like SK, right, then it is even larger data set, and there they won't even be able to store all the bytes that they observe. So they will be, yeah, that's a radio telescope. So they will be taking data. Square kilometer array is actual receiving area in the radio is 1 square kilometer. So all the data that they'll be taking, there'll be various correlated algorithms that will be run, and only the interesting seeming bits will be stored, whereas the rest will be thrown away. But there are again interesting things. When you go to space-based thing, Gaia is a mission, European mission, that started taking data very recently, and the transients are starting to come out only now. I think about 20 or so have been published so far. So they, because they're space-based, the technology had to be decided upon several years earlier. And the way they send down the data is that they don't send down 2D images, but it's squished down to 1D images. And when the next time satellites goes along, it goes along a different direction. So all these different directions are put together, and the 2D image is somehow recreated. So there are instances of those kinds too that come into the picture. But enough parallelization and intelligence will help us solve the data. LSST itself is an interesting question, because it's the timeliness in which we want the data to be out, right? Meaning all the, so LSST's mandate is that the analysis will be done and the transients released within the minute of the data being taken. So that is the crucial part. In many other cases, that's not so.
There is a lot of combination that underscores the point. It's not just the advantage of this knowledge, but the incentive. Look at all the security of data, featured algorithms,
Yes.
characterization, taxonomy,
Mhm.
etc.
Absolutely, yeah. That is going to be still a vital thing. But many of the curation parts could still be assisted by machines to to start with, to a great extent. So, it will make your life easier. It may not completely do that. But yeah, absolutely, you can do that, and there have been various experiments. So, there is this setup called the Eureka, where you could give it data and it will come up with equations for you. We have written a paper on it also. So, there is something called fundamental plane of elliptical galaxies in astronomy. We were able to rediscover that. It gave us slightly different equations, but similar enough that they were believable. But what happens also with neural networks or deep networks, if you don't know the physical meaning, what it's pointing to, then it becomes difficult. So, interpretation becomes difficult. But fine, you can start with throwing big computation at big data and get some quick meaningful results out, and then spend more time interpreting that, and that may help you in defining new features, definitely. So, that is possible now.